All right, my friends, let's take a look at example one. There are many ways to do example one. So first I'm going to review the way that we've learned in the past, and then we'll talk about a totally different way you could have been taught for part A. And then when we do that, it'll transition fairly nicely into part B. So for part A, what have we learned in the past, right? We've learned to diagnose, right? So in this case, to get from 3 to 5, you add 2. To get from 5 to 7, you add 2. 7 to 9, you add 2. 9 to 11. Okay, so this thing's arithmetic, right? And so the formula for the nth term that we have that works is take the first term and then basically point out that, hey, you just keep adding 2's. And how many 2's would you need to add to get to any nth term? Well, n minus 1 of them. And then if you simplify this, you would get, 3, let's say 2, what would that be? 2n plus 1, I believe. There we go. So that's a way to do that problem. Now I want to talk with you about another way that you could also do the problem. You will not prefer it, and that's fine with me. But then the method that I'm about to demonstrate carries the strategy carries over to part B really well, and you actually need the strategy in part B. So I guess you should listen to this part. Anyway, so another way that you could have been taught to do part A would have been, let me erase this to give myself some room, would have been to basically notice that if your first, these are called your first differences. So if your first differences are constant, then that would mean that you're going to have a linear model. And I'll just comment on why that makes total sense in just a second. So if your first differences are constant, that implies that you're going to have a linear model. And why does that make so much sense? It's not even funny. Well, because if you were to graph this where you've got an n axis and an a sub n axis instead of x and y, then your first term was 3. Your second term, you increased by 2 and got to 5. Your third term, you increased by 2 and got to 7. So, yes, it's a linear model, right? And the common difference would be the slope of your equation. And so hopefully that makes sense. So I'm going to give myself some room again here. But anyway, so yeah, it's a linear model. That makes total sense, right? And so basically, you could have learned this to say, okay, well, I know that the model is going to be of the form, instead of like mx plus b, maybe you'd have like, your common difference. No, without even actually, could we even just like pretend you don't even know that that's the common difference? Anyway, you could just say like a times n plus b, I guess. Maybe I don't want to use a there. Let's use m times n plus b. There you go, like mx plus b, but instead of x, you have an n. And then you could have basically taken these points, right? So that 3 that you have there, that's like saying a sub 1 is 3, right? And so that would be like saying, so if you put 1 in for all the n's, and then n would be plus b, and then a sub 1 is 3, and then you could simplify this, and it would say 3 equals m plus b, which is 2 unknowns, and so you'll need 2 equations, and so you could go to your next number, which is 5, and you could say, oh, well, a sub 2 is 5. And so if I plug that into this model, then that if n was 2, it would say a sub 2 is m times 2 plus b, and I could replace a sub 2 with 5, and that would give me the equation 5 equals 2m plus b. And if you hate this, that's okay, because we had a way better way to do this that was way faster. So you're not supposed to like this for part A, but you are supposed to be able to follow it. Anyway, so now you have a system of equations and you could solve it using substitution or elimination. So like I personally would multiply row 1, that is, by -2. And then I'd add it to row 2. And we'd get b equals 1. And once you know that b is 1, you could use that and back substitute into either equation. I like row 1. And then row 1 would then tell you that 3 is equal to m plus 1. And whoops, m plus 1. And that means m is equal to 2. You hate it, don't you? I hate it too. Anyway, and then once you know what m and b are, you would take them and you'd back substitute into your model that you were using. And so you'd say, oh, a sub n is 2 times n plus 1. Isn't that awful? Anyway, that is a way harder way to do part A than what we learned earlier. And so after that demonstration, if you do a problem like part A this way, someone might point and laugh at you, just so you know. Okay, but hopefully you at least follow that, because that strategy you're going to need for part B. So check this out. So for part B, let's start diagnosing, right? 3 plus what is 5? 2. 5 plus what is 8? 3. Wah, wah. Not arithmetic, right? So we don't have a linear model. 8 plus 12, you'd have to add 4, and then you'd have to add 5. Okay. So your first row of differences is not constant, which means you would not have a linear model, aka it's not arithmetic. Well, it's not geometric either. And so what you could do is you could look at your second row of differences. So like, what would you do to get from 2 to 3? You'd have to add 1. From 3 to 4, you'd have to add 1. From 4 to 5, you'd have to add 1. And so since your second differences are constant, that would imply, I wonder if you have a guess, that instead of a linear model, you'd get a quadratic model for your nth term. So that strategy that we used for part A starts becoming pretty necessary for part B. So you'd start with a general quadratic. A sub n could be a times n squared plus b times n plus c. So notice this is like saying y equals ax squared plus bx plus c. And then you could take term by term, just like we did before, and you could put it into this model. So like a sub 1 is 3. So if you put 1 in for all the n's, it would say this. And then from there, a sub 1 is 3. So you put a 3 there, and then you simplify the right side. It would just say a plus b plus c. Oh no, we have 3 unknowns. Well, that would mean that we need 3 equations, but that's okay. You just keep going down the row and using the terms. So a sub 2 would be 5. And so that means if you go back to this general model here and just put 2's in for all the n's, that would tell you, that would yield a sub 2 is 5, so put a 5 there, and then simplify the right side. And then a sub 3 is 8. So if we go to the base model here, and then put 3's in for all the n's, then simplify, a sub 3 is 8. Whoops. Put 3's in for all the n's. There you go. And now you have a system of equations with 3 equations and 3 unknowns, and you get to solve that. using your favorite method, and I highly recommend using elimination. So this will be some good review for some of you. So survey the A's, the B's, and the C's, knowing that whatever you choose to eliminate, you need to eliminate twice. You need to make sure you involve all three equations. So I personally would choose to eliminate the C's. So I would get, let's see, and I like keeping my numbers low. So I'm going to blend row 1 and row 2. So I'm going to take the opposite of row 1, and I'm going to add it to row 2. And notice that the C's will get eliminated here. I'll just double underline it so that I know to come back to it. Now remember, you do need to involve row 3, and you need to eliminate C again. If you choose to eliminate C the first time, you need to eliminate C the second time. So I'm going to do, and I like to keep my numbers low, so I'm going to do the opposite of row 2 this time, which would be -5 equals -4a minus 2b minus c, and I'm going to add that to row 3. I would end up with 3 equals 5a plus b. Now the plan is, now that I've got basically these two equations, this is like a new system of equations, and I just need to find where those two lines in 3D space would intersect, just by using elimination again. So I'm going to call this first one equation 1 and the second one equation 2. I'll even write it down. Actually, no, I won't write it down. I'm too lazy. All right, so I'm going to do the opposite of equation 1, which would be -2 equals -3a minus b, and I'm going to add that to equation 2. Like so, I'd end up with 1 equals 2a. Divide both sides by 2, and you know that a is 1/2. Once you know a is 1/2, back substitute into one of the equations that just had 2 letters in them to figure out what your other one would be. And so it doesn't really matter which one. I like equation 1 just a little bit better. So if you back substitute 1/2 in for a, you'd have something like that. And then 3 times 1/2 is 1.5, subtract it over, and it looks like I'm getting b equals 1/2 as well, which makes me feel a little weird about my math, but oh well. Okay. And then once you know your b term, then you could go back to any of the first 3 equations where you had 3 unknowns. I like the first one personally for simplicity matters, and you put a and b back in and solve for your last letter. So that would give you 3 would equal, a is 1/2, b we found to be 1/2, and then we're about to find c. So simplify, 1/2 plus 1/2 is 1, subtract it over, and it looks like we're going to get c equals 2. All right, so we got a, b, and c. And now it's just a matter of trying to remember what the heck we were supposed to do here. So we were supposed to figure out a quadratic model that would generate the terms. And so you're going to go back to your original quadratic model and just back substitute your a, b, and your c values for your final answer. So a sub n is equal to 1/2 n squared plus 1/2 n plus 2. Okay, and now because I got a little weirded out with a and b being the same thing, because I don't remember that being the case, I'm going to check and see if it works. So if I use this model, according to my model, a sub 1 would be 1/2 times 1 squared plus 1/2 times 1 plus 2, which would simplify to be 3. Right, well, it's at least generating my first term. All right, a sub 2 would be 1/2 times, just drop a 2 in for n. All right, let's simplify that. 4 times 1/2 is 2, plus 1 plus 2, and that would be 5. So this model generates a 5 for your second term. Oh, goodness gracious. Okay, so I'm actually feeling pretty good. And just if you're like super paranoid, you could make sure that it would give you an 8 when you put 3 in. This is for folks who are very paranoid. Let's see, 3 squared is 9, so you'd have 9 halves or 4.5 plus 1.5 plus 2, 4, 5, 6, 7, 8. Woo! Woohoo! Anyway, so there you go. I've triple checked it that actually is the rule that you'd use to generate the terms. So, okay. So, just a quick review, my friends, of the process. Check your first differences. If your first differences are constant, like in part A, then you're looking at an arithmetic, and you could just do it like we did in the past with the formula that we learned back earlier in chapter 8. If, however, your second row of differences are constant, then you will need to use a quadratic model. And then it leads to a system of equations of 3 unknowns where you'll need to remember how to solve that kind of thing. And then once you get your A, B, and C values, you make sure that you go back and complete your model to write your final answer. And you can always check your answer like I demonstrated here. And just for food for thought, what kind of model do you think you'd get if your second row of differences were not constant, but your third row was constant? Just a little food for thought. All right, my friends, I hope the problem set goes well, and I hope if it isn't going well, you're willing to ask me questions to make it go a little better. Take care, everybody.